Every year, millions of tons of animal-derived fibers move through industrial systems like this. By the time wool reaches storage, its quality has already been decided. What looks uniform here hides a long Hebraeus. Industrial systems move wool efficiently, but not gently by default. Every movement is the virtuous. Wool survives manufacturing only when restraint is applied early. Storage preserves quality. Dekrost.
Automation reduces human error, but not mechanical risk. Even here, handling forces are limited in prefaces. This is the final destination for finished yarn. But the most important decisions happened long. Wool appears soft and forgiving. In reality, it is mechanically unforgiving. Once damaged,
Conditions. Wool begins as a biological fiber grown by living animals. Sheep are the primary source for global wool production forms here. Each fiber forms with a specific length, diameter, and natural wave. These properties the sievers. Other animals also grow usable wool fibers. Goats produce fine, long fibers used in specialty towels. Fiber length is a mechanical advantage. Shortened fibers permanently. No later walkers fibergris. Alpacas produce dense, fine fibers with different mechanical behavior. Despite variation,
at this stage, the fiber is still intact and continuous. Its future strength already exists here. Before machines, before automation, wool is grown, not made. Every industrial decision.
Shearing is the controlled mechanical removal of wool from the animal. The objective is not speed, but continuity.
A clean shear removes wool without breaking fiber length. Excess force creates invisible damage. Riverlace. An intact fleece signals mechanical restraint. The fiber network remains continuous, do not announce themselves. They travel forward silently through the process. Factories only reveal them later. At this moment, the wool is complete. Its usable length is already fixed. Nothing downstreams. Fiber integrity is visible only when examined closely. Breaks introduced here weaken everything that follows. Once removed, the fiber is no longer biological. From this point on, it is industrial material. Fresh wool is handled with minimal force. Friction at this stage causes permanent fiber damage. Gentle handling preserves mechanical tolerance. Nothing is cleaned yet. The goal is containment, not processing. Every unnecessary movement increases risk. Compression is unavoidable for transport, but pressure must be limited. Excess fits. Once tied, the bale's condition is locked. Internal damage cannot be inspected or reversed. Mechanical handling replaces human hands. Shock loads are avoided deliberately. Fiber failure begins. Transport does not improve wool. It only preserves or degrades what already exists. The fiber now waits for its first industrial transformation. Every decision so far is scouring is the first irreversible industrial step. Its purpose is removal, not improvement. Anything damaged here is lost permanently. Heat, water, and detergent dissolve natural grease. Temperature is controlled tightly. Mechanical action is limited on the purpose. Excess agitation causes felting. Once fibers locked again leaves the system here. What exits with the water will never return. What remains must stay intact. Rinsing stops chemical action. Timing matters more than force. Delayed rinsing continues damage invisibly. Global systems rely on repetition and consistency. Uniform handling prevents uneven fiber failure. After scouring, the wool is clean and exposed. Its natural protection is gone. From this point on, drying stabilizes the fiber for mechanical handling. Moisture must be reduced but not eliminated. This balance defines future flexibility. Heat is applied indirectly. Direct heat damages fiber structure. Even drying preserves elasticity. Drying occurs in stages. Rushing this step creates brittle fibers. Brittleness cannot be reversed later. Water leaves as vapor. Fiber damage does not announce itself. Only later stress reveals it. Properly dried wool regains flexibility. This condition is temporary. Next process. Fiber separation as reduces internal friction. Reduced friction lowers risk. Moisture is now within tolerance. The wool is ready for mechanical processing. From here on,
Opening begins the mechanical phase of processing. Its role is separation, not alignment. Excess force here weakens fibers permanently.
the spikes apply controlled mechanical stress. They separate clumps without shortening fibers. As fibers separate, internal friction decreases. This reduces breakage risk downstream. Blending creates batch consistency. It does not average out weakness. Any damaged fiber is deformity prevents localized failure. It does not increase strength. It only ensures predictable behavior. From this point on, fiber paths narrow. There are fewer opportunities to remove defects. Mechanical difference. Opening is preparation, not transformation. The fiber is exposed and vulnerable.
Parting introduces direction. Fibers are no longer random. Alignment begins here.
The drums comb fibers into parallel paths. Mechanical stress is unavoidable. Alignment improves future strength, but it exposes weak points. Short fibers begin to fall away.
Carding selects by survival. Weak fibers are removed permanently. They cannot be reintroduced later. The sliver is the first stable structure. Its consistency defines downstream stability. Errors here.
Handling must remain gentle. Twisting or tension introduces stress. Tolerance margins are narrow.
At this point, fiber selection is complete. Only suitable fibers move forward. The rest are gone forever.
The woolen system retains short fibers. It prioritizes bulk and air retention over strength. Mechanical tolerance must be reduced to compensate. Drafting is intentionally limited. Excess stretching would snap short fibers. Restraint traps air. Air provides warmth without added weight. This structure sacrifices tensile strength. Yarn structure is set immediately. Bulk is locked in permanently. Later processing cannot tighten it. Winding applies final tension. Even here, force is limited deliberately. Fiber slow spurts. Low-speed operation reduces stress. Production rate is sacrificed for integrity. Woolen yarn is complete at this stage. Its properties are permanent. Strength limits are already set.
The worsted system removes short fibers. Only long fibers continue forward. Material loss increases strength.
Combing is selective by design. Short fibers are removed permanently. This decision can reduce tensile strengths. Alignment increases strength. Parallel fibers share mechanical load. Uniform sliver prevents stress concentration. Irregularity causes localized failure. Higher drafting improves fineness. It also increases breakage risk. Control margins are narrow. Worsted yarn locks alignment through twist. This structure resists abrasion. Errors cannot be undone later. At this point, material paths diverge permanently. Woolen and worsted yarns behave differently forever. Drawing combines and evens out fiber streams. Its purpose is uniformity, not strength. Stress must remain evenly distributed. Controlled stretching improves alignment. Excess tension snaps fibers silently. Breakingless. Parallel fibers share mechanical load. This reduces localized stress. Consistency is locked at this stage. Variation introduced here cannot be corrected. Sensors detect deviation, not damage. They cannot repair broken fibers. They only prevent further loss. Gentle coiling prevents twist and tension. Premature twist locks defects in place. Timing matters here. Drawing is the final preparation stage. From here, fibers are committed to becoming yarn. Spinning locks loose fibers into yarn. This is a point of no return. Once twist is applied, structure is permanent. Twist binds fibers together through friction. Too little twist weakens the yarn. Too much dotelgux. This tightening distributes load across fibers. Uneven twist concentrates stress. Tension guides control force precisely. Excess tension snaps fibers invisibly. Tashmingermits. Winding completes yarn formation. Uneven reduces weak zones. Synchronization reduces sudden load changes. Consistency prevents localized fiber failure. At this moment, fiber becomes yarn. All mechanical decisions are locked in. Nothing.
Fresh yarn must stabilize before testing. Residual tension relaxes slow. This pause prevents false measurements.
Tensile testing measures breaking strength. It reveals cumulative damage. It does not identify. Uniform thickness indicates stable processing. Variation signals hidden fiber failure. Visual inspection catches surface defects. It cannot see internal weakness. Quality data summarizes the process. It reflects past decisions, not current ones. Means suitability, not perfection. Limits are accepted here. Nothing can improve the yarn further. Rejected yarn cannot be repaired. Its fiber history is irreversible. Manufacturing only allows packaging does not change yarn quality. It only protects what already exists. All mechanical outcomes are already fixed. Wrapping prevents moisture exchange and abrasion. It cannot reverse fiber fatigue. Protection replaces handling force is still controlled. Even finished yarn can be damaged. Mechanical tolerance remains limited. Sealing marks the end of production. Nothing beyond this point alters the yarn. Manufacturing authority ends here. Distribution begins immediately. Logistics assumes stability. It depends entirely on earlier restraint. Automation reduces variability. It does not reduce past damage. Consistency cannot replace care. The yarn leaves the factory unchanged from this moment on. Its future performance is already determined.
Consumption begins inside other factories. Textile machines assume fiber integrity. They cannot compensate for weakness.
Weaving applies repeated tension cycles. Weak fibers fail first. Failure appears grievances. Fabric quality reflects yarn history. Uniform rolls indicate stable processing. Pilling begins at weak fiber ends. These ends were created long before fabric existed. The cause is never local. Garment production assumes consistency. It cannot remove internal defects. Every cut reveals prior decisions. In use, wool degrades gradually. This degradation follows mechanical memory. The fiber does not fail by chance. It fails according to how it was treated. Manufacturing restraint defines longevity.